So in this part, we are going to focus on method used to animate virtual character. And we will first start by describing how skin deformation is computed from a so-called animation skeleton. Then we will see how the animation of the character is actually handled. And finally, we will see a short point on the generation on crowd animation. And let us first start on the case of deformation of the skin of a character. The most common approach to animate a character is related to something called skeleton-based deformation. The underlying idea is that characters and creatures are mostly articulated ones, as they are generally made with some internal bone structures that define limbs that are moving under the action of the muscle. The process consists in defining a skeleton that is used to control the degrees of freedom of the limbs, and then use the skeleton to deform the skin of the character. So this approach is often called skinning. And the articulation itself of the limbs is set via rotations around the joints. So more formally, an animation skeleton is composed from a set of frames, TI, that are defined by a position and an orientation, and often organized as a tree structure. Each frame can describe the non-rigid parts of the character, or in other words, its degrees of freedom. Straightforward analogy, we call a joint the frame TI, and we call bone the segment between two consecutive joints. Note that the animation skeleton is not necessarily linked to the anatomical skeleton. For instance, on this model of cat, lots of bones that are only segments are in the head of the model, while there is much fewer in the body. Actually, this can be explained by the fact that animating the head of the model requires more degrees of freedom, like the nose, the mouth, each eye and ears can move independently. And we need, therefore, one joint per element that can be controlled individually. Now let us wonder how we can map the deformation of the skeleton, which is basically described by rigid transform, to the skin of a character described by a mesh. The simplest possible idea is to attach rigidly a subset of vertex to a specific bone. And then all vertices attached to this bone follow the deformation of the frame. For instance, on this image, all green vertex are associated to the bone on the top of the leg, and the vertices in red are associated to the bottom one. Let us see how we can formalize this approach. So we consider that we have a rest pose state where we typically perform the vertex attachment. In this rest pose, the frame representing the joint has coordinates given by the 4x4 matrix T0, or a rotation and a translation, which is similar. And we consider a vertex V0 attached to this frame. During the animation, the joint undergoes some transformation and ends up as being a new frame T. This new frame can also be represented as a 4x4 matrix, and this matrix is the coordinate of the unit vector of this joint and its position with respect to the global frame. And the deformed vertex position of the skin has coordinate V. So now the question is, how can I express the new coordinate V with respect to T, T0, and V0? Actually, there is several ways to find the answer. One way is to look at the local or relative coordinate of V and V0 with respect to their respective frame T and T0. We can represent the relative coordinates of V0 with respect to T0 as T0 inverse times V0. And during the animation, as the vertices are rigidly attached to the frame, actually the relative coordinates of V remains the same with respect to T. So V is not moving in its local frame. So then we can say that the relative coordinates of V, which are T inverse times V, is actually equals to T0 inverse times V0, which end up to the relation expressing the V coordinates, which is equals to T times T0 inverse times V0. Another way to find this expression is to say that v is actually the deformation of the coordinates v0 by the transformation that map t0 to t. And this transformation matrix M is actually expressed by t times t0 inverse. And we end up with the same formulation. So this method has some advantage. First, it allows to articulate an arbitrary mesh on a skeleton, which is something easy to build and quite intuitive to manipulate. Using skeleton, we really have the feeling of manipulating directly the limbs of a character. However, using the rigid skinning formulation leads to artifacts, as the deformations are piecewise rigid. There is a sharp angle of the deformation at every articulation, which leads to self-penetration of the surface and large elongation. So how could we solve this issue? And this is the idea of smooth skinning, and this idea is to blend the multiple and discontinuous transformation around articulation into a single one. And so this leads to the formulation of the so-called linear blend skinning, or LBS in short, that consists in interpolating linearly the position between different frames. So let us look at this example of cylinder that contains two joints and bones, B1 and B2. The problem related to the rigid skinning mostly appears at the junction between the two bones. In this case, it's in the middle of this cylinder, and we consider the point P0 to be initially in this middle. So we bend rigidly the cylinder using these two bones. Then the top part of the cylinder rotates, while the bottom part stays fixed. And the point P0 can have two different positions depending whether we attach it to the joint B1, this is the position P with respect to B1, or to the joint B2, this is the position P with respect to B2. With smooth skinning, we say that there is no more reason to belong to a bone than another. So one thing we can do is to take the point which is in the middle between P with respect to B1 and P with respect to B2, and this gives us the point P we show. Now we can also formalize what we just did. Basically, we said that P is equals to 0.5 times P with respect to B1 plus 0.5 times P with respect to B2. As P with respect to B1 and P relative to B2 are given by rigid skinning, we can expand these temporary points with the previous formulation we just saw. So we have P is equals to 1/2 T1 times T10 inverse times P0 plus 1/2 of T2 times T20 inverse times P0. And we can call T1 times T10 inverse as the transformation M1, and similarly with M2, and factorize the point P2. Then we have P is equals to 1/2 M1 plus 1/2 M2 times P0, which states that actually smooth skinning blends linearly the matrix of deformation associated to each joint. Of course, in this case, we did the derivation with the middle point. So we use the contribution 1/2 and 1/2. But if we look at the entire cylinder, we can extend this approach to smoothly varying contributions. At first, the vertex in the bottom will mostly depend on B1 until reaching the middle, where it is shared between the two joints. And then in the top part, the vertices depend more on the joint B2. So this interpolation can be characterized by some weights, alpha, and in this case we would have P is equals to alpha of P with respect to B1 plus 1 minus alpha P relative to B2, or P is equals to alpha M1 plus 1 minus alpha M2 times P0. So alpha is called the skinning weight and describes how much a vertex is influenced by a given joint. We can even generalize more, as we can have shapes with more than two bones, and in this case we call alpha k the dependence of a vertex to the joint k. And the final position is given by P as the sum over all the joint k, of alpha k times p with respect to bk, or in its matrix form, p is equals to the sum of all the joint k of alpha k mk and the result applied to the point p0. And to preserve a correct global transform, the weights alpha need to sum up to 1 to distribute their influence, and all the weights should also be between 0 and 1. And so this is the general formulation of the smooth skinning. P is equals to the sum of all the bones of alpha k mk p0, or extending the transformation matrix to their respective frame coordinates, we have P is equals to the sum of all the bones of alpha k times tk times t0 k inverse times p0. And this smooth skinning is actually the very standard for almost all articulated character deformations. It provides very intuitive type of deformation based on skeleton. The deformed shape is controllable through the skinning weights, and it's very efficient to compute, as we can see that it's mostly relying on blending matrices and apply matrix vector product. And it can be easily computed entirely on the GPU. As a result, this approach is heavily used in animation, cinema, and video games. Almost all characters are animated using skinning. So for the history, this method has been initially mentioned in 1988 in research and started to be known in industry around the end of the 90s. So I mentioned the fact that the deformation can be controlled by the skinning weights, which are this dependence between a given vertex and the joints. So for each vertex, we may have up to n weights, where n is the number of joints of the skeleton. Of course, in practice, the dependence is often sparse, and a given vertex has only few non-zero weights for a few joints. Video games often limit the number of dependencies to 6 or 8. But how can we generate these values of dependence? One way is to paint them manually, and basically all 3D modelers like Maya or Blender propose directly dedicated interfaces to paint your skinning weights directly on the surface using brushes-like tools. Note that this can be actually more complex than it appears, as the weights are not only like painting a color, but they are barycentric coordinates, which means that if you increase the dependence of a weight with respect to a joint, the dependence with respect to all the other joints is going to decrease. And remember that the sum of the skinning weights for a given vertex must always sum up to 1. So at the end, even if there is a graphical interface to help, correct skinning weight painting can require an expertise in itself and is often done by expert artists. And this process of attaching the dependence between the mesh geometry and the controller of the motion is called more generally rigging. And you can find in companies artists that are expert to generate rigs. Another approach is to try to generate these weights automatically. A simple idea is to say that the more away a vertex is close to the segment of the bone, the more its dependence should be high with respect to this bone. We can consider the closest Cartesian distance between the position of the vertex and the bone that we call d. And then we take into account the inverse of this distance. So like that, the closer we are from the bone, the higher will be the weight. As the sum of the weights need to be normalized to 1, then we can normalize the result by the sum of the inverse distance with respect to all other bones. This approach is quite fast to compute and can give good first guess of skinning weights in several situations, typically in tube-like limbs. Of course, using such automatic computation will not be perfect in all cases. Actually, one of the most complex parts to handle correctly in a human character are the shoulders, as we have specific rigid parts from the anatomical bones, so the deformation should not be symmetric, and the influence of the body position is harder to model correctly, as multiple joints are actually involved. But in most situations, a first guess of skinning weights can be automatically computed, and then refinements on local part of the character can be added by the artist using painting approaches. Another note on the automatic computation using the Cartesian distance is that the influence of the bones doesn't take into account the morphology of the shape, which means, for instance, that if we have two legs close to each other, we may consider the influence of the bone of the right leg to the vertices of the left legs and conversely with left to right. So to limit such issues, most of the models in early time were provided in a position where the limbs are the more far away as possible, typically with the arm and the legs like fully extended, and this was called the T-pose that we can still encounter today. Of course, we can also consider more advanced ways to compute the weights, typically in taking into account the limit of the volume bounded by the mesh, or in considering weights that are diffused over the surface using a Laplacian diffusion, for instance, instead of considering a Cartesian distance in space. And here is a few words about the file format for skinning deformation and animation. When we consider a static mesh, there is very common and standard formats, such as OBJ, PLI, or OFF, that has simple format to read and parse, and are quite dedicated to handle meshes. And this makes the exchange of mesh files actually quite easy. When we go into the world of animation and skinning, unfortunately, these things become more complex. There is less open and simple format to store animation data in a simple form. Actually, we encounter more generic format aiming at storing entire 3D scenes. So this format can handle skinning, but also many other information, like storing multiple objects. It can handle multiple skeleton, different type of interpolation, but also the material properties, the texture, the shaders needed to display a scene, the position of the camera, the lights, and so on. So this genericity comes at a price, which is that these formats are much more complex to parse and use correctly. So in the open and ASCII readable format, we can find Collada, which is an XML norm, and GLTF from Khronos Consortium, the same than OpenGL, and use a JSON language. There is an example of Collada and JSON format on the slide, and if you look at them, you can see that they contain quite a lot of information, and they are therefore harder to parse than simple mesh storing file. And of course, almost all 3D software come with its own internal file format. It can be FBX, blend files, 3ds, and so on. And these files are often encoded in binary format, and they require dedicated framework to parse them. So we saw that skinning is highly used to animate character, but it's not perfect. The first limitation we already saw is the fact that the weights can be complex to define. And another limitation are the artifacts on the geometrical deformation when using large angles. These artifacts are so common that they have specific names. The first one happens when we twist a limb at 90 degrees, leading to a singularity in the middle. And it's called the candy wrapper effect, with its similarity to the wrapping paper on a candy. And the second is visible when we bend the limb. There is a visible loss of volume around the articulation, which is called the collapsing elbow effect, as it's often visible in the elbow of characters. Now we can think about the origin of this issue. Why do we have such artifacts? Actually, if we go back to the initial formulation of the skinning, we saw that it's a linear blending of transformation matrices. This is one of the advantages of the method, as it's very fast to compute, but if we think about it, it's also something we shouldn't do. Remember that for rotations, we should not try to interpolate them using linear blending between matrix coefficients, as it would involve spurious scaling and shearing. But this is exactly what we are doing with linear blend skinning. We blend linearly the coefficient of the matrices of rigid transform. And this explains why we have these artifacts with scaling and even singularity issues. In the case of the candy wrapper, for instance, all coefficients of the linear part cancel out, and we have a scaling by a factor 0. So what can we do to improve the situation? We know that we should avoid to linearly blend between rigid transformation or more generally affine transformation matrices. So the first naive idea would be to apply the interpolation we saw for key poses in time, but in the space domain. We can split the transformation matrix into a rotation part and a translation part separately, and we can blend the rotation part using quaternion and translation part linearly. Unfortunately, this approach will not work for such deformation in space. For a nice deformation, we need to have a continuity of the center of rotation around the limbs. This is obtained by default when we use linear interpolation, but if we use quaternion blending and translation blending separately, the center of rotation around which the deformation takes place doesn't necessarily follow the trajectory along the skeleton. Remember that this center of rotation is actually linked to both the rotation part and the translation part. And then you can have this type of results that looks much worse actually than linear blend skinning if you apply this interpolation. So a possibility of improvement is to actually compute an optimal center of rotation and constrain the deformation to act accordingly. This was proposed in 2005, but actually a more general and systematic approach has been found 2 years after. And it relies on the use of something called the dual quaternions. So the dual quaternions is the generalization of quaternions to dual numbers. So a dual quaternion is an element q hat that is equals to q0 plus epsilon times q epsilon, and epsilon is called the dual element. So first remember that quaternion is already the generalization of complex number to 3, and dual quaternion themselves extend this idea of quaternion, but to handle both rotation and translation in a single entity, and it's well adapted to handle motion along rigid transformation. Actually, the use of dual quaternion model rigid transformation as screw motions, which are motion composed of a rotation around an axis, followed by a translation in the direction of this axis. So what are actually these dual numbers? So a dual number in its general form is a number A, which is equals to A0 plus epsilon times A epsilon, where the dual element epsilon is nilpotent, which means that epsilon is not equal to 0, but epsilon squared actually is equals to 0. So this can look strange, but it shares the properties of what we use for infinitesimal quantities. When we have a dx, for instance, we suppose that dx is different from 0, but dx squared can be assumed to be 0. And actually, as epsilon is related to differential quantity, its main use in computer science is in automatic differentiation. Typically, you can find all the laws of differentiation between numbers using this dual number formalization. And playing with that, you will have the value of your number in the real part and the differential component on the dual part. So, in our case of dual quaternions, we write this dual quaternion q hat is equals to q0 plus epsilon times q epsilon. The parameter q0 will encode the component of the rotation, and q epsilon will encode somehow the part which is related to the translational component. And without going into all the details, actually we can have a correspondence between rigid motion and the associated dual quaternion as follows. We suppose that we have a unit quaternion, q0, which is the rotation of the rigid motion, and a translation t equals tx, ty, tz. The associated unit dual quaternion corresponding to this transformation is given by q hat as q0 plus epsilon divided by 2 qt times q0 with qt given by tx, ty, tz and 0 coordinates. You can see that there is actually a clear resemblance with the correspondence between quaternion and axis angle. And this form is actually the normalized form of a dual quaternion that has a unit norm. And it describes the set of rigid transformation as screw motions. If we go further into the analogy with the axis angle representation, we can even define a dual axis and a dual angle and express this dual quaternion in its standard form cos theta divided by 2 plus n sinus theta divided by 2. And in this case, the dual angle, theta hat, is such that its real part is the angle of rotation, and its dual part is the magnitude of the translation along the axis n0. And for the dual axis, n hat, we have n0, which is the standard axis of rotation, and n epsilon is called the moment of the rotation axis. So we saw that we can convert a rigid transform to a dual quaternion. And now how can we convert a dual quaternion to its rotation and translation part? So we have an arbitrary dual quaternion which is not of unit norm. Q prime hat, which is equals to Q0 prime plus epsilon Q prime epsilon. And we want to normalize it and extract the correct component part. So for that, we can identify the dual quaternion to its parametrization in unit norm and as rotation translation part. The first step is to normalize the non-dual component, and this is the standard normalization in quaternion space. So we can write Q0 is equals to Q0 prime divided by the norm of Q0 prime, where Q0 is a standard quaternion. And then we identify with the parametrization of the dual component. We have 1/2 of Qt times Q0 that has to be equals to Q epsilon prime divided by the norm of Q0 prime, which means that Qt has to be equal to 2 times Q epsilon prime times the conjugate of Q0 divided by the norm of Q0 prime. And now we have all the elements to perform the skinning with the dual quaternion, which is also called DQS. First, we have as input a set of rigid transform per join, given by quaternion and translation. We convert these into their dual quaternion correspondence, which is Q hat equals to Q0 plus epsilon divided by Q, Qt Q0, with Qt being the quaternion with the translation coordinate Tx, Ty, Tz, and 0. Then we perform the actual blending as a linear interpolation in the dual quaternion space, and this is called the SCLERP as a screw lerp. So we have Q prime hat, which is equals to the sum of all the bones of omega times Qi hat, with omega being the skinning weights. And then we can normalize this blended dual quaternion and extract the rotation and translation component. So we compute a new dual quaternion, Q hat prime prime, in normalizing it with the norm of its real part. And then we can identify the rotation part. And secondly, we can extract the translation component from the product 2 times Q epsilon prime prime times the conjugate of Q0. And finally, once we have the rotation and translation, we can apply them to the vertex position to generate the deformation. And here you can see the difference. The dual quaternion skinning actually fully solves the candy wrapper effect. Now we have a smooth twist instead of the singularity. And the collapsing elbow is not there anymore. Actually, the joint has a more pronounced and rounded bending transform, and the volume is not shrinked anymore. It's actually pushed a little bit outward. So with respect to linear blend skinning, dual quaternion has some nice advantages. First, it really solves the candy wrapper artifact, and it allows smooth twisting motion. With respect to computation, it's also very efficient, almost as efficient to compute a classical linear blend skinning, and all computation can also be performed per vertex on the GPU. But it's actually not always better than linear blend skinning, and we saw in bending deformation, actually it creates a kind of bulge which may not be wanted. In this character, for instance, the bending of the knee looks better with the linear blend skinning than with dual quaternion skinning. Also, dual quaternion skinning is not always better, so as a result, dual quaternion skinning is not always better than linear blend skinning. So both solutions are actually proposed in standard tools, and artists can choose between linear blend skinning and dual quaternion depending on the effect they want to achieve.